If you spend any time studying electricity, you've likely come across two different ways to describe electric fields. There's Coulomb's law, which is the classic inverse square law, and there's Gauss's law, which might look more intimidating due to the integral sign and vector notation. It may not be obvious at first glance, but it turns out that these two laws actually have a lot in common. Welcome back to Infinite Insights. In the next 5 minutes, we're going to prove that Coulomb's law can be derived as a direct logical consequence of Gauss's law without using any hard calculus. If you've ever wondered why gravity and electricity drop off by exactly r squared and not r cubed, this is the answer. Let's start by familiarizing ourselves with Gauss's law. Here, the integral symbol with the circle simply means that we are looking at the total flow or flux of an electric field through a closed 3D surface called A. This kind of surface is also called a Gaussian surface. The law tells us that the total flux is strictly determined by how much charge is trapped inside that surface. If there's charge inside, field lines punch through the surface and we have a net electric flux. If there's nothing inside, the field lines go in from one side and out the other, leaving the net electric flux at zero. Now let's derive Coulomb's law. We start by assuming the electric field from our point charge is spherically symmetric. This means that the field strength is the same at every point on the surface of the sphere, and it always points directly outward. This assumption holds for a stationary point charge. Since a point charge is symmetric in every physical direction, the field it produces also looks identical regardless of how you rotate your point of view. Because of this perfect symmetry, the math becomes incredibly friendly. Since E and our area vector dA are always pointing in the same direction, the dot product reduces to a scalar product of magnitudes. Again, we can exploit the symmetry of the electric field. Since E is constant at any fixed distance from the point charge, we can pull E right out of the integral. Now, what is the integral of dA over the surface? It represents the sum of all the area elements over the entire surface of the sphere. So it's just the surface area of a sphere, 4 pi r squared. Solving for E, we get the field strength at distance r. E equals q over 4 pi epsilon naught r squared. This expression for electric field embodies Coulomb's law. It tells us the strength of the field created by charge q at any point in space. The electric field strength E at a point in an electric field is defined as the electric force experienced by a small positive test charge placed at that point divided by the charge. In other words, E equals to F divided by Q. If we want to know the magnitude of the force exerted on a second charge Q, we simply multiply the magnitude of the field strength by the charge of that second particle. Physicists simplify this expression by grouping the constants together. We define Coulomb's constant, Ke, as 1 over 4 pi epsilon naught. This gives us the classic force equation that you might recognize from most physics textbooks. Finally, we can get the more rigorous vector form of Coulomb's law by attaching the radial unit vector. For like charges, the resulting force vector points outward along this direction, and for unlike charges, the force points inwards, attracting them. And now you have a visual understanding of how Coulomb's law is actually a logical consequence of the geometry of space. If you found this breakdown helpful and you want to keep exploring the math behind the physics, make sure to hit that subscribe button and join us here at Infinite Insights. Thank you for watching, and I'll see you in the next lesson.